Okay, welcome guys. So we'll keep going, maybe showing some examples, showing some results about close and open. Okay, so we still need a lot of definition. So definition, right, so X is also a matrix space. Again, E is a subset of X. And so E prime is just denoted as all the limit point of E. So remember what limit point is, that which points basically, if any open neighborhood will intersection with E, not just the point itself, right? So this is a definition of limit point, and I define closure to be E union the limit point. So a simple example will be if this is open ball, then the closure will be just, so this ring, right? This boundary is a limit point. So this open ball, this closed ball will be open, will be the closure. Okay, so this is called closure. Okay, so theorem. I think this theorem is commonly used, but we should remember the proof. So as in the matrix space is subspace, so A is E bar is closed. So closure is closed. Okay. Okay. The second is that E, if E is the same as closure, then if only if E is closed, right? C is that so E bar F for every, so let's assume that you have let's assume that your E closure is a subset of F, and for every closed set F, subset of X, such that E F E is a subset of F. So what I'm saying is that if F is closed, so if F is closed, and E is a subset of F, then E closure will be subset of F. Okay. Okay, so A is E bar is closed, right? So we need to prove closure is closed. So A. So proof, let's say you pick X, right? P belongs to X, and your P is not E bar, right? So that means you pick some X which is not closure, and then we need to prove that so we just want to say what? We just want to say P is not limit point of E, right? Because I want to prove that P is, I want to prove that oh sorry, yeah, so I just want to say that P is not limit point of E bar, right? Because E bar is already contains limit point, so P is not limit point. So not limit point means you can find a neighborhood, right? You can find a neighborhood, let's say N, right? So such that P belongs to N, and the N intersection with the N intersection with E only contains P, right? So only contains P. Right, so this is because P is not a limit point, right? Okay. But which tell you what? Which will tell you that P is open, right? P is open. So sorry, now I should say E bar C, right? Because any points in the E bar complement, you can find neighborhood which do not intersection, do not intersection with E, right? Also not intersection with right, do not intersection with E. So do not, if it that, so also do not intersection with E bar, right? Because there's no limit point, right? So E bar complement is open. So by definition, now how we already proved, so E bar is closed. Okay. Okay, so if E is E bar, right, then by definition, by A, right, so E bar is closed, right? So E is closed. Okay. Yeah, we only, so somehow like we only prove yeah. So what I already I say is that E equals to E bar, then E is closed. So somehow I only prove this direction, right? So I want to prove that if E is closed, right? But by definition, closed means that all the limit points, right, E prime belongs to E. It's a subset of E, right? So which E bar is union E prime, right? So which is the same as E. Okay, so this is just a definition. Okay, so C, I want to prove that if F is closed, so for any closed set, if F cover E, then F will cover its closure. Okay. Let's see, right? So if E cover F, but F is closed, right? So F will cover F prime itself, right? So we can see F cover F prime, right? By definition, there's this thing that I want to mention. So notice if E subset of F, right, and then E prime will be subset of F prime. Okay, this is definition. This is by definition, right? Because for any E prime means that for any points you draw a ball, which that ball intersects with E, not only P itself, right? But the E is a subset of F, so it must intersection with F prime. It must be also a limit point. Okay, so from this, this is just this is, I think this is whatever is said is said. This is true, right? So so now F is cover F prime, right? So let's see. So F, right? So we got this, and this E bar, right? E bar is E union E prime, right? So this guy F prime, right? This guy is F, right? But so E bar is subset of F union F prime, right? But the F prime is a subset of F because F is closed, right? So this is F. So closure contains in F. So that's definition. So let's see. We take Y. Suppose we have this, and suppose. So definition. Suppose we say that is relatively open. Y, right? If for P belongs to E, there exists R greater than 0, such that Q belongs to E whenever dPQ less than R, and the Q belongs to Y. Okay, so let's say that if E is relative open to Y, if for any P belongs to E, there exists a ball, right? Such that if Q belongs to E, when PQ distance is less than R, and the Q belongs to Y. Okay. So that means you can forget about X and somehow show that if somehow if you have the radius R such that in this ball is forcing Y, so it's not forcing X but forcing Y. So you can somehow forget about the X. Okay, so this is called relatively open. Okay. Yeah, this is okay. So theorem. So theorem says that take a subset of X, the subset of E of Y. So a subset E of Y is relative open. So yeah, so this is the we already say, right? There is a rigorous definition for relative open. Is relative open if only if E is Y intersection with G for some open set G. Okay, so what we are just saying that this theorem just tell you that the relative open notion somehow so abstract, we can just view E just some Y intersection with open set G for some open set Y intersection with G for some open set G. Okay, so proof. So let's prove this direction. So if E is open relative to Y, so it's open relative to Y. Means what? That means like to each p, right? So for every p belongs to E, you can find the RP, right? So so-called RP, such that if your PQ less than RP and the Q belongs to Y, right? You will implies that Q belongs to E. Okay. So that means, right? Definition means that you can find RP, right? Such that given P and the right. So if your Q is less than the distance less than RP and the Q belongs to Y, right? Then the Q will belongs to E. Okay. Okay. So we can just define. So let's define VP. Right? Let's define open set. So let's define VP a set of Q such that the DPQ less than RP. Let's see. Yeah, so VP is defined to be Q and the Q belongs to X, and DPQ less than RP. Right, so you pick up you fix P and ask all the element in X such that the BPQ less than RP. Okay, so take all the VP and define G to be all P belongs to E and the BP. Okay, union. Okay, so so G is open. G is open. Why? Because this is open, right? This is open. The open was open, right? So any union is open, so G is open. Okay, so P. Okay, so notice that obviously P belongs to VP, right? Because the radius 0, so which tell you that P belongs to G, which you tell you that E belongs to E is a subset of G intersection Y, right? Because because P belongs to G, right? So this E is just G intersection with Y subset. Okay. Okay. So our choice also tell you what? Our choice also tell you that this VP, right? By definition, this VP intersection with Y is a subset of E. Okay. For every P belongs to E. Okay, so here's tell you that G intersection Y, so you just take the union, right? So this become G intersection Y is the subset of E, so E is just G in intersection with Y. Okay, so this is one direction. So conversely, let's say G is open, right? G is open in X, right? And the E is G intersection Y. Right, so every P, right? So every P belongs to it. One can find open ball, right? Okay, find open ball which is a subset of G, right? By definition, because G is open, right? So obviously that one can restrict it. One can intersection this VP with original Y. Okay, so one can choose YP. So one can see YP intersection with Y is a subset of E, right? So this is VP, right? So because VP is a subset of G, and so VP, right? So VP is subset of G, right? So VP, right? So VP intersection Y is subset of E. So from this, you know that E is relative open. E is relative open. Open to Y. Okay. That's it. See you guys next video.